Good evening and welcome to another Monday night calculus stream. I've got a really cool problem to talk about. It's going to tie together some math that you've seen in Calc 2, some math that you definitely have not seen in Calc 2. And it's just a lot of fun. And after that, I will gladly take questions about any and all Calculus 2 topics. But why don't we dive right into this problem. It's called the Brachistochrone problem. It comes from the Greek words meaning shortest time. And the idea is that if I have 2 points, I want to find the path between them. Like imagine building a track and running a marble down it. I want to build my track to get the marble from point A to point B as quickly as possible. Breadman the man, welcome. I'm glad you were excited for some cool math. So you might try building just a straight line track from point A to point B. This does minimize the distance between the 2 points, but it's actually not the fastest path. Something else you might try is this sort of path here that drops really quickly at the beginning, so the marble is going to pick up a lot of speed, and then in this long horizontal section it'll be going fast because it dropped in height substantially at the beginning. That'll probably be faster than the straight line. Another option is you could even go down below the height of B, so the marble will get going really fast. But of course, the more I pull the path down, the longer it has to travel. So it's going faster, but it has to go farther. So what path is going to balance out these factors and give us the shortest possible time? That is the question. Okay, so in order to minimize the amount of time, we need to first write down an expression that computes the amount of time. And, it probably won't surprise you to learn that this is going to involve an integral. This is how we've been approaching all of the applications of integration in Calc 2, is we've been thinking about just one little bit of the problem, one little moment in time, maybe one little slice of a tank of water, one little bit of a chain. In this case, we're going to think about one little bit of time corresponding to one little section of this track. And it's going to take some small amount of time dt, and then we add up all of those little bits of time, like for this section and this section and this section and this section. We add up all the little times it takes for the marble to run through those little sections, and that's the total time. Okay, so this is nothing interesting yet. I've just said that t is the integral of dt. But now we're gonna rewrite this in a way that involves the velocity. So I'm going to use s to represent the distance along the track. And so ds dt is going to be the speed of the particle. Jacob, hey, welcome. Glad you could join us this evening. Is that a cheer? Is that a bit? I'm new to the Twitch stuff. I don't. Wow. Okay, you've cheered one bit. That is the first bit that has ever been cheered on this channel. It's a bribe. Jacob has yet to to make a request, so it's not a bribe yet. But thank you for the 1 bit. Okay, so the velocity or the speed is going to be ds dt, and I'm going to rewrite that as dt equals ds over v. Okay, so t is going to be the integral of ds over v. This is going to get a lot more complicated before it gets simpler. Okay, so there's going to be some physics involved, just a little bit at the beginning, because we have to think about how gravity is influencing the particle here, or the marble. So we're going to use conservation of energy. And the point is that the marble's speed only depends on how far it has descended. So I'm going to use a coordinate system where y actually points downward. That's just going to make the math a little bit simpler. And I'm going to set the origin of my coordinate system so that y equals 0 is at the top. So again, if you're not particularly knowledgeable about physics, don't worry about that. I'll tell you what physics tells us about the situation, and then we'll move on from the physics and just investigate this using the tools of calculus. But conservation of energy is going to tell us that the particle's kinetic energy, which is 1/2 mv squared, is equal to the potential energy that it's lost by descending to a lower height, which is mgy. So again, this is all the physics that we need to know. From here, it's just math. Exam 2 is going to be a struggle. Yeah, we'll start thinking of questions that you'd like me to talk about once I get through my fun problem here. Now, in this equation, I can cancel out the m's on both sides, so the mass of the marble doesn't matter. And I just have 1/2 v squared equals g times y. I'm going to solve this for v so that I can replace that v up in the integral with this expression. So I'll multiply both sides by 2, and then I'll take a square root. So v is the square root of 2gy. So that handles the v. We also need to rewrite this ds. And that's something that should be familiar from your study of arc length. So the ds can be written in terms of y and y prime. And by y prime, I mean dy dx. So the goal here is to figure out this function, the shape of the curve, by expressing the height, y, as a function of x. Okay, so I'm using the Pythagorean theorem here. The point is that if we have a little section of the track, which is basically a straight line, and the length is ds, well, if the height is dy and the width is dx, the Pythagorean theorem tells us that ds squared plus equals dx squared plus dy squared. And then I'm going to factor out a dx squared on the right side. And actually I can just write this as dy dx squared. Hang on, let me rewrite that in the next line. And actually that's just y prime squared. So now if I take the square root of both sides, I get ds equals the square root of 1 plus y prime squared times dx. And again, this should look familiar because this is how you compute arc length. Really the only difference between this and arc length is that for arc length, you just integrate ds. Here we're integrating ds divided by the velocity because that tells us not just the length, but how much time it takes the particle to move through this small area. I'm just realizing now that a little bit of this is cut off on the screen. Sorry about that. Is that visible now? There we go. Let me catch up on the chat. Oh, Jacob, yeah. So, are you seeing some Calc 2 stuff in applied probability? I keep I've heard this often about the applied math department. I don't know anything about their courses, but they sound like a lot of fun. Okay, so we've rewritten both v and ds. So now the time is the integral of ds over v. The amount of time it takes the marble to roll from one end to the other is the integral of ds over v, which is the integral of root 1 plus y prime squared over v, which is 2gy. Oh, and I forgot the dx, but I'll just put that here. Okay. So where are we going to go with this? I guess there's just one little thing I want to do, which is to pull the constant 1 over root 2g outside of the integral. It's not going to be really important for the rest of what we're doing. But this is an expression that computes the amount of time it takes the marble to roll down the track, and our goal is to minimize this. Now, you've taken Calc 1, so you should have an idea of how to minimize something. Oh, good question. Don't I want to write ds in terms of dx dy since my v has y? Yeah! That's a good thought. I'm expressing this in terms of y, so you might think that I want to have an integral with respect to y. But this situation is just weirder than anything you've seen before in the calculus. Part of the weirdness is I don't just have a y here, I also have a y prime. And if I write this in terms of dy, I'll end up with an x prime instead. So there's something very weird here, which is that I have the derivative inside my integral. And there's another really weird thing, which is in a normal calculus optimization problem, you have a function and you're trying to minimize or maximize it, which means you're trying to just decide on one number, the input to the function, which results in the greatest or the smallest possible output. This is a much more complicated situation. We're not just trying to determine one single number to optimize something. We are trying to decide on an entire function. Right? We don't know what this y of x is going to be. We are trying to find a whole function which goes into this integral, both the function itself, y, and its derivative y prime, and we're trying to minimize that integral. So let me write that. Unlike a typical calculus optimization problem, we're trying to choose not just one number, but a whole function. To minimize the output. And so we'll need a more advanced technique than simply setting a derivative equal to 0, finding some critical numbers. So yeah, it's a very long answer to your question, turn one knot Pagel, but writing it in terms of dx dy, it would still be very complicated. I haven't tried working it out that way. I'd be curious to see how the details work out. So how do you choose the function that minimizes this integral? Well, this is really a whole subject called the calculus of variations, and it's a complicated subject. I'm not going to get into all the theoretical details. I'm just going to kind of tell you what the main tool is for answering this question, and then we'll apply the tool. So this tool is called the Euler-Lagrange equation. And it says essentially that to maximize or minimize let me rephrase this. A function, let's say y of x, that maximizes or minimizes the quantity, it's an integral, and I'm writing L of x, y, and y prime just to mean our integral is some expression that involves y and y prime and possibly x. In this case, we actually don't have any x's appearing in this expression, and that makes things quite a bit easier. But to minimize an integral where you don't know what the function y is, that function has to satisfy the Euler-Lagrange equation, which looks like this. The derivative with respect to x of the partial derivative with respect to L, or of L with respect to y prime, is the partial derivative of L with respect to y. Now, these partial derivatives with the funny looking d's are not a thing that you've seen in calculus up to this point. They're a topic from Calc 3, but it's a pretty simple topic. It's not scary. I'll walk you through how this computation works, but it's not something to be afraid of. And I made this point that our function here only involves y and y prime. It does not explicitly involve x. And that makes the situation slightly easier. And I could write this in the language of partial derivatives, meaning that the partial derivative of L with respect to x is 0. So this Euler-Lagrange equation actually takes a simpler form, which is just that L minus y prime times the partial derivative of L with respect to y prime is a constant. Okay, this probably looks very confusing and mysterious. I'm not going to spend any time talking about where this equation comes from, how you get from that one to this one, why this is the way to minimize it. I'm just going to try to show you how this tool gets applied, and if this is a topic that you're interested in, if you're curious to know more details, I'd invite you to dive into this in more depth. The buzzwords to Google are calculus of variations or Euler-Lagrange equation. But we will be plenty busy tonight just applying this equation. So in our example, trying to find the Brachistochrone, this function L, which depends on x, y, and y prime, is this expression here, the square root of 1 plus y prime squared over the square root of y. Okay, so the Euler-Lagrange equation tells me that this thing is going to be a constant. So I'm first going to compute this partial derivative. Okay, so the partial derivative of L with respect to y means I'm differentiating this expression, which is L, with respect to y. And normally when you differentiate something with multiple variables, right, y prime depends on x, y depends on x, y prime, I guess, depends on what y is. You have to apply the chain rule when variables depend on each other. It's complicated. But the partial derivative is nice because it tells us we don't have to worry about that. Sure, y prime depends on what y is, but I'm not actually even going to think about that. I'm just going to pretend that y prime and y are totally unrelated variables. And in fact, when I differentiate with respect to y, with a partial derivative, anything that's not y prime, I'm going to pretend it's a constant. So first of all, this 1 over y prime, the root y, the square root of y in the denominator, that's not a y prime, so that's a constant. It comes outside of the derivative. Okay, now I'm trying to take the derivative of a square root of something. Square root means that thing to the 1/2. So the power rule says I pull down the 1/2. I have that thing to the negative 1/2 power. But then the chain rule, I do need to use the chain rule here because I'm differentiating with respect to y prime, and there is in fact a y prime inside of the square root. So I differentiate that inside function with respect to y prime. And now when I clean this up, the derivative with respect to y prime of y prime squared is 2y prime. How can we take y as a constant? That's a great question. It's because, you know, and again, I'm not going into the details of why this equation works, but what this equation tells us is to use a partial derivative. And what a partial derivative means is that whatever variable you're differentiating with respect to, which in this case is y prime, you pretend everything else is a constant. That's just what a partial derivative means. So, maybe as a side note, if I were to take the partial derivative with respect to x of this expression, now if this were a normal derivative, if these were actual d's instead of these funny squiggly d's, y depends on x, y prime depends on x, that derivative would be a bit of a mess to complicate. It's magic, yeah, exactly. But in this case, I don't literally see the letter x in here, so this is just 0. Yeah, partial derivatives are magic. Okay, so I can actually even simplify this a little bit, because these 2's cancel out. Anything else that I can simplify? Maybe I'll just write this. I have the 1 over root y, and then I have this thing to the negative 1/2, which means it's in a square root inside the denominator. Okay. Just looking at my notes to make sure I haven't messed anything up yet. Alright, we're good. So now the equation says that L minus y prime times that partial derivative is a constant. Alright, so it says L minus y prime times this partial derivative is a constant, and L was that thing, so root 1 plus y prime squared over root y times, or minus y prime times this partial derivative that we just calculated, which is y prime over root y root 1 plus y prime squared. So this whole thing is a constant. We are making progress. It might not look like it. But this actually simplifies. I have 2 fractions here. So to combine them, I'm going to get them over a common denominator, which all I have to do is multiply this first fraction by root 1 plus y prime squared over root 1 plus y prime squared. And then in the numerator, the square roots go away, and I just have 1 plus y prime squared. And in the denominator, I have root y and root 1 plus y prime squared. Stuff is about to cancel. Over in the second function, I can bring that y prime up into the numerator, so I have y prime squared. In the denominator, I have a root y, a root 1 plus y prime squared. And when we subtract these fractions, these things cancel. So we are just left with 1 in the numerator. So 1 over root y, root 1 plus y prime squared is a constant. I can make this look even nicer. I'm going to take the reciprocal of both sides. So on the left side I get root y, root 1 plus y prime squared. The reciprocal of a constant is just another constant. Okay, why don't I square both sides? On the left side I get y times 1 plus y prime squared. A constant squared is just a different constant. And at this point, let's give a name to the constant. So I have y is 1 plus y prime squared. It's going to be equal to some constant k. And, you know, I haven't told you anything about why this Euler-Lagrange equation gives us the correct answer to the problem. This is just a tool that I've presented to you, and I claim that it works. But notice what it's done for us, is it's given us this equation. This is a differential equation. This is progress. Before we just had some integral that we were trying to minimize by choosing the function y of x, but now I actually have a differential equation for y of x. This is something that we can solve. And even better, this is not any old differential equation. It's actually a separable differential equation, which is really the only kind of differential equation that you've studied in Calc 2. So yeah, how do you solve a differential equation? We're going to rewrite that y prime as dy over dx, and then we're going to get all the y's on one side and all the x's on the other, and integrate. Okay. Let's see. So, in order to separate this, I'm going to have to get the y prime by itself. So I'm first going to divide both sides by y, and then I'm going to subtract 1. It's actually going to help me with the algebra later on if I go ahead and write this 1 as y over y, and then combine the fractions to get k minus y over y. So same thing we did up here. I'm just getting a common denominator in order to subtract these two fractions. And I guess now I can just take the square root. So we learned that y prime is root k minus y over y. And let's go ahead and rewrite that as dy dx. So dy dx is root k minus y over y. And well, I'm going to multiply the dx over to the other side, and then divide both sides by this root k minus y over y. And the reciprocal of a fraction, well, yeah, if I divide by this fraction, that gives me the reciprocal. So I'm going to end up with y over k minus y dy. And now we integrate. Just integrate both sides. So I get x equals the integral of y over, or the square root of y over k minus y with respect to y. So again, we've made huge progress here because we have x equal to, some integral of y. So if we can just do this integral, it might be hard, but at least this is a concept that we're familiar with from Calc 2 and even Calc 1. We'll get x equal to some function of y. We really wanted y as a function of x. That's fine. We can figure out how to invert this function to get y as a function of x instead of x as a function of y. But first we'll need to do this integral. So you've seen some integrals with square roots previously in this class. And what's your technique normally for doing an integral that involves a square root? There are a couple of things you might try. Chain rule. Well, you would need the chain rule if you were differentiating. Sort of the reverse of that for anti-differentiating is u substitution. And the u sub is one of the first things you should try. I don't see a u sub here that's going to do this easily. Try u equals k minus y. I don't think this is going to help too much, but I'm just curious to see what this does. You should never be afraid to just try something. So I'm going to get the square root of k minus u over u, I guess times minus du. Which is just not much better, because I still am going to have a k over u inside the square root. Hey, Mean Machine Rex. How are you doing tonight? Rewriting dy dt times dt is chain rule. Yeah. Yeah, I guess I'm just not seeing how to apply a chain rule here to turn this something into more doable. Trig sub is, these are all great answers. Trig sub happens to be the right answer here. Like when you saw things with a square root of something plus x squared, you tried substituting x equals tangent of, or a tangent of theta. When this was a minus sign, you tried a substitution with a secant. If these, or sorry, a cosine or a sine. If these were the other way around, you tried secant. This is what we have here is not quite any of the situations that you saw with trig sub. Yes, there's a suggestion in chat to rewrite this as k over u minus 1 and do a trig sub here. It's still not obvious to me how, like, this is not obviously any of the trig subs you've learned about, because the variable is in the denominator of a fraction inside the square root. I'll tell you what trig sub ends up magically working here, but I wanted to at least sort of motivate like why a trig sub is the right idea. So the trig substitution that happens to work here is we're going to let y equal half of that constant k times 1 minus cosine theta. Magic. Inverse hyperbolic something. Yeah, I don't even know. I didn't come up with this on my own. I looked up a way to solve this problem. This is how my source did it, and I worked through all the details myself, and it does work. So the point is that I guess what is this even valid to do? Well, sure. Cosine theta can be as big as 1, so this expression can be as small as 0. So I guess this thing can vary between 0 and 2. And if our constant k is big enough, we'll be able to make sure that that this y value can actually take on the full range of values between the height of a and the height of b. And yeah, just to find some sort of transformation between y coordinates and theta. Turn 1, Nat Pagel. We shall see, but I'm curious where your intuition comes from. This is not something that I would have had any intuition for when I was taking Calc 2. I'm just curious. Let's see. Every cool melon, can I explain how to convert between r theta axis and the xy axis for polar coordinates? Yeah, I'd be happy to talk about that once I get through this problem. It's in the textbook. Oh. Okay. Wait, you read the textbook? I didn't know people actually read the textbook. I'm glad to hear that. Oh, I guess. Yeah, okay. Yeah, because your textbook is pretty useful. Yeah, I think it is. I certainly recommend that everyone reads the textbook. I just, I think a lot of people get by in Calc 1 and Calc 2 without reading it, which just means I think we provide you with such great resources in our classes that it's not always necessary to read it, but certainly I recommend it. Okay, so yeah, if you're doing polar coordinates, you might actually have seen this equation very recently. Okay, so I guess the first thing I should do is I should compute dy, because I will need that for the substitution. The derivative of minus cosine theta is sine theta, d theta. Okay, so if I continue this here, if I make the substitution, I'm going to get x equals the integral of the square root of k over 2 times 1 minus cosine theta over k minus y. I actually want to simplify k minus y over on the right side. I'm not going to try to do it inside the integral, inside a fraction, inside a square root, inside the integral. It would just get too messy. But let me simplify this. K minus y, we're saying y is k over 2 times 1 minus cosine of theta. If I distribute that k over 2, I get minus k over 2 plus k over 2 cosine theta. And then k minus half of k is just half of k. And I can pull out the k over 2, and I'm left with 1 plus cosine of theta. Okay, so that denominator here, the k minus y, is k over 2 times 1 plus cosine of theta. And the dy is k over 2 sine of theta d theta. Penn Center, hello. We've got a Canadian viewer. Wow. Yeah, sorry the match didn't go your way a couple days ago. But thanks for joining. So, like with any good trig substitution, was that a couple days ago or was that just yesterday? I don't know. I didn't watch the game. But like with any good trig substitution, this looks terrible right now, but like everything is going to cancel out. Okay, so I mean, first of all, these k over 2's cancel out, so that's nice. I'm going to pull the other k over 2 from over here outside of the integral. And let's just rewrite this with all that cancellation and shifting around of constant multiples. Don't follow sports. I don't really follow sports either. But I do watch a lot of Olympics coverage for these 2 weeks every 4 years. Teams that are poor in sportsmanship. Oh, I was talking about hockey. Are you talking about curling there? Let's see. Or is the hockey team also? I don't know. Okay, so when I see something like this, I mean, alarm bells go off in my head, and I really want to try multiplying by the conjugate, which in this case would be 1 minus cosine theta. So I'm multiplying by the sort of the conjugate of the denominator. And that's not a precise term, it just refers to this idea of changing the plus to a minus, because we're going to end up with a difference of squares. I don't think either team is a paragon of sportsmanship. Oh, what? I don't even. Yeah, I don't know what happened. I really don't follow a lot of sports. I watched a lot of figure skating and a lot of freestyle skiing. Let's see. So in the numerator, I have 1 minus cosine theta squared, which is great because I have a squared and then a square root, so those are going to cancel out. In the denominator, I have 1 minus cosine squared of theta. In chat, can you tell me what I can do with 1 minus cosine squared of theta? Sine squared theta. Rev 66 has got it. That's the most important trigonometric identity. That is equal to sine squared of theta. And now I trust that you can see how this is going to simplify. That square root is just going to turn this into 1 minus cosine theta over sine theta. And it's better than that because I also have a sine theta floating around outside of the square root. Those are going to cancel. And all that I have to integrate in the end is 1 minus cosine theta. That's easy. The integral of 1 is theta. The integral of cosine theta, or minus cosine theta, is minus sine theta. If I'm being careful, I should think about the constant of integration. I'm not going to worry about that right now, because I'm not going to worry about the details of like how to actually match up the curve that we get here. It is a cycloid, by the way. Whoever was it turn 1 nap Hegel, you were correct. It does end up being a cycloid. I'm not going to worry about the details of like how to match up the cycloid with the 2 points here. But if I wanted to do that carefully, I should probably involve the constant of integration. But we're just going to sort of look at this cycloid with these equations here. Um, But this interesting thing has happened, which is that because we made this substitution involving theta, we now actually have a parameterized curve, which is that x equals k over 2. And you know what? I'm just going to write a instead of k over 2. It's just a different constant. So x is a times theta minus sine theta. And you know what? We're used to using t for the parameter, so I'm just going to rewrite theta as t. It doesn't matter what I call my variable. And y equals, let's see, it was a times 1 minus cosine of t. So here are these equations. And this figure is called a cycloid. I will show you a graph. So let's hop over to Desmos and see what this looks like. It's super cool. So I have plotted here this cycloid. You can see up in the top left. Those are the equations we just worked out for the x and y coordinates. It looks about like this. And the really cool thing about this is, sort of if I trace this out over time, there's a really nice way to describe this curve, which is I'm going to put a circle here, and we're just going to let that circle roll along the x-axis at a constant rate, and I'm marking that one point that started out at the origin. If we trace out, are you all ready? This is so cool. If we trace this out, trace that point as the circle rolls along the x-axis, the curve that it traces out is this cycloid. Is that not the coolest thing you've ever seen? Oh hey, all of the other math streamers are joining us now. Actual Education, e to the 2i pi, welcome. Big Ducky Snow, wait, first time chat from Raider? Did I get rated? Whoa, I've never been rated before. This is awesome. 13 viewers? Wow, thank you for the raid. What were you up to today, Actual Education? So many first-time chatters. Wow. Don Factorial, thank you for following. JCYW, thank you for following. Jacob, you followed me half an hour ago. And Rev, you followed me half an hour ago. I forgot to thank you. So I will now. Thank you for following. Gladiator Leos, thank you for following. 50 followers! Big Ducky Snow, thank you for following. I just reached 52 followers. This is incredible. CU Boulder Calc 2 is getting popular. Yeah. Alright, Penn Center's got a fun fact. I have to read the fun fact. You can make a bike have square wheels and it will work smoothly on the cycloid surface. It's just like flipping, right? The circle is, the tire is round, and that works on a flat surface. But if you make the tires have flat sides, then it works on a cycloid surface. That's cool. I think I saw a bike like this with square tires at MoMath, the museum of modern mathematics in Manhattan. Yeah, that's a super cool thing. Gamma and beta functions. Ooh, that's exciting. Um, oh, maybe it's a catenary? There's some sort of curve that works perfectly with square wheels. Let me Google. Inverted catenaries. Yeah, so you don't actually have a cusp there. But if you go to the Wikipedia page square wheel, there's an excellent GIF or GIF, whatever you say, of a square wheel rolling smoothly over some inverted catenaries. Oh, there was an XKCD about this recently, right? Here, I put the link to the XKCD in chat. Yeah, a circle in the 1/2 norm. Wait. Or is it the max norm? A square and the max norm would be a circle. Soup norm. I feel like my real analysis professor made that joke about like limb soup. That probably sounds really weird to anyone who hasn't taken analysis. Okay. Yeah, it's limb soup. The limb is without a B. Can I go for a work problem? Yeah, in a little bit. Someone else asked about something about polar coordinates. I don't remember the precise question. Well, JCYW, thanks for joining us. Have a good night. We got a second vote for a work problem, so we will add that to the queue. It's 4 a.m. Where is it? 4 a.m. Is that the UK time zone? Converting rectangular to polar. Yeah. Okay, so let's finish up this problem. I guess we found the curve. I wanted to do two things with this real quick, which is I want to look at one little arch of this cycloid, and I want to find the arc length. And I want to find the area underneath. Because, well, yeah, arc length is a topic that you all learned about recently. And integrating in different coordinate systems, I think that would be really valuable. I'm sure, yeah, you all are doing some integration in polar coordinates. Okay, so let's find the area underneath one arch of the cycloid. Do I want to do area first? Sure. Okay. So how do we find area underneath a parametrized curve? I don't remember if this is something that you do in Calc 2, here at CU Boulder at least. But let's just look at one little section of the curve. And we want to find the area underneath that little bit. Now this is basically a rectangle, or at least I can make this little rectangle, and it doesn't matter whether I use the left endpoint or the right endpoint to get the height of the rectangle. When I do an integral, it's not going to matter. But what's the height of this rectangle? The height is y. I guess I should label my axes. But the height is y, and the width is dx. Oh, Big Ducky Snow, thank you for that suggestion. I did not know about this. Okay, so what have I been saying this week, last week? How do we compute things in Calc 2? We solve a very small problem, and then we just add up all the solutions. So this little area is y times dx. That's the area of the rectangle. What's the total area? Sum them up. So we're going to integrate y dx. We do need to do a definite integral. These are parameterized in terms of t. So I'm going to give the bounds for t. Since I'm giving t bounds and not x bounds, I'm going to write t equals. What are the t values going to range from? If I pop back over to Desmos, for one arch here, that t goes up to about 6.2. Anybody know any numbers that are close to 6.2? Also, right, the t value here is representing sort of, how far the circle has rotated. So one full rotation, yeah, it's actually closer to 6.28. And in fact, one full revolution of that circle, that's 2 pi. Okay, I have expressions for x and y. So y is a times 1 minus cosine of t, and dx, let me make a little note in the side here, dx is a times, well, the derivative of t is 1, the derivative of sine t is cosine of t, and the dt. Important not to forget that dt. So if I copy down the dx, that's a times 1 minus cosine of t dt. This is going to work out beautifully. I've got an a squared, and then a 1 minus cosine of t times 1 minus cosine of t. I'm going to go ahead and expand that out. That's 1 minus 2 cosine t plus cosine squared of t. I can pull the a squared outside of the integral. And you all learned how to integrate functions like cosine squared of t earlier this semester. In case anyone's forgotten, let me remind you. This is also one of my goals with these streams, is to sprinkle in little bits of review throughout the semester. So that's, to help you retain some of the stuff from earlier semester, so that you don't have to relearn it all in the few days before the final exam. So the way we integrate a cosine squared, which is the only term here that's difficult to integrate, is we use the identity cosine squared of t is 1 plus cosine of 2t over 2. So I have 1 minus 2 cosine of t plus 1 plus cosine of t, of 2t over 2. If I divide this and split this fraction up, I'm going to get 1/2 plus this 1 makes a total constant term of 3/2. I have a minus 2 cosine of t, and then I have a plus 1/2 cosine of 2t. And now I can write down an antiderivative. It'll be 3/2 theta minus 2 sine of t. Theta? Whoops. I abandoned theta a long time ago. That should be a t. Minus 2 sine of t plus 1/4 sine of 2t. And this gets evaluated from 0 to 2 pi. And the really nice thing about evaluating things at 0 and 2 pi is if they're a trig function, they give you the same results. As long as you're not doing like t divided by 2. And these are just sines. Yeah, when I plug in 0 or 2 pi, these are all 0. The only term that's going to survive is this 3/2 t. So I'll get 3/2 2 pi minus 3/2 times 0. This comes out to just a squared times 3 pi. So 3 pi a squared is the formula for the area underneath one arch of this, not catenary, cycloid. There we go. Alright. And now let's find the arc length. Arc length is definitely something that you've done in in parametric curves. That arc length, once again, it's an integral from t equals 0 to t equals 2 pi. And you could write this a few different ways. The one that's going to be convenient here is the square root of dx squared plus dy squared. Yeah. Like, yeah. Yep. Okay. So, we found dx previously. dy is even a little bit simpler. The derivative of that 1 is 0, and the derivative of minus cosine t is positive sine of t. Dt. Let me copy this. For convenient reference. Okay, so dx squared is a squared 1 minus cosine of t squared. dy squared is a squared sine squared of t. Oh, and they both have a dt squared, but I'll factor out the dt squared, and then it gets square rooted, so it just becomes a dt outside the integral. Oh, I guess another way that you might see this written is just the integral of dx dt squared plus dy dt squared with respect to t. Same thing. Okay, I need to simplify this. So that's 1 minus 2 cosine t plus cosine squared t, and then plus this sine squared of t. The a squared gets square rooted, and then it can come outside the integral. And then that cosine squared t plus sine squared t is 1, which combines with this 1 to make 2. So I'm left with 2 minus 2 cosine of t. Now, how do we integrate this? Just like with this cosine squared of t, we're going to use that same trig identity, almost that same trig identity. We're going to use the other one. Sine squared of t is equal to 1 minus cosine of 2t over 2. I'm using that one because it has a 1 minus cosine. Now I'm going to do a little substitution here. I'll write this with theta instead to make this substitution a little more clear, but I'm going to replace theta with t over 2. Right, this identity is valid for any value of theta, so I can just plug in t over 2. Is a greater than 0? Yeah. Yeah. You're being a little more careful than I am, worrying about, when I pull an a squared outside of a square root. Do I get a or do I get minus a? But yeah, a is greater than 0. Okay, so sine of t over 2 is equal to 1, sine squared is equal to 1 minus cosine of 2, cosine of t. Yeah, if theta is t over 2, then 2 theta is t. Then I'm going to multiply both sides by 4. because then I get 2 times 1 minus cosine of t, which matches what I have here. And then we end up square rooting both sides. So when all is said and done, this square root is equal to, that is equal to this. Sorry, that's going off the screen. I keep forgetting that I don't have my full screen on here. Alright, does that fit now? Yes. Okay, so this is equal to this, which is equal to that, and when I simplify that square root, I just get 2 sine of t over 2. And my antiderivative here is 4 times minus cosine of t over 2, which gets evaluated from 0 to 2 pi. So it's a times minus 4 cosine of 2 pi minus 4 cosine of, oh, sorry, it's not 2 pi because it's t over 2. So when I plug in 2 pi for that t, I just get pi. Cosine of pi is negative 1. Cosine of 0 is 1. So I get a times 4 plus 4, which is 8. And I guess I should also point out, this a value here is what it's representing is the circumference, sorry, the radius of that circle. You can see when I have a set to 1, the circle has a diameter 2 and a radius of 1. So the length, the arc length of one arch here is 8 times the radius of the circle. How can I do a triangle inequality in L2? That's a really interesting question. Not directly related to this, so I'll have to answer that for you another time. Alright, any questions about this Brachistochrone problem or the cycloid? It seemed very hard. Yes. I hope that most of the individual steps made sense, but it is definitely a lot. But I think it's so cool that we can take this question where, you know, we have no idea what the correct shape is to minimize the time, and we can do some math that I have not fully justified for you, but we apply this tool, we get a differential equation, we solve the differential equation. Woo! That is a lot of work, and we get this really cool curve, the cycloid. All right, why don't we take a short break here, and then I will answer questions. So converting between polar coordinates and rectangular coordinates, that was one, and then work was the other topic. So during the break, if you all could help me out by sort of making your questions a little more specific, that would be helpful. Like for converting between coordinates, do you want to see like conversions with just like the coordinates of specific points? Do you want to convert equations between one form or the other? For the work problem, was there a particular type of work problem you'd like to see? So why don't we take like a 10-minute break? I've been talking for like nearly an hour and a half, so let's just take a 10-minute break. Go outside, get some fresh air, rehydrate, and leave me a message in the chat if there's like a specific kind of work problem you would like to see. Um, and I will use the break to maybe look for a couple examples. But any specific work requests, just throw them in the chat during the next 10 minutes. And I'll see you back here at 9:30. All right, we're back. So let's talk about converting between rectangular and polar coordinates. And then we'll do some work problems, or at least set them up. Okay, so let me just remind you of the relationship between these two coordinate systems. X is equal to r cosine theta, and y is equal to r sine theta. And really everything comes from this picture. Right? SOHCAHTOA, by definition, cosine of theta is x over r. If you rearrange that, x is r cosine theta. And then the Pythagorean theorem tells you that x squared plus y squared equals r squared. And another thing I know is that the tangent of y over x is theta. So these are the equations that we use to convert between coordinate systems. So let me do some examples. So let's go Cartesian to polar. And let's do the point, let's say 3 root 3 comma 3. I might even draw a right triangle. I'm actually going to make this slightly more interesting. I'm going to make this minus root 3. There's a reasonably common mistake that you might make here. So I want to do a slightly more difficult one. So the triangle is going to look something like this. Now r squared is still going to be x squared plus y squared, which is minus 3 root 3 squared plus 3 squared. 3 root 3 squared is 9 times 3. Yeah, that's going to be 27. And then 3 squared is 9. 27 and 9 makes 36. So r is 6. Theta. Well, what do I know about theta? I know that the tangent of y over x is theta. Sorry, that doesn't make any sense. Y over x is equal to the tangent of theta. No one in chat said anything. You all gotta call me out when I write silly things. Tangent of theta is equal to y over x. So in this case, tangent of theta is 3 over minus 3 root 3, which is just minus 1 over root 3. Now if you want to find the angle, we can take the arctangent of minus 1 over root 3. And that's going to be minus pi over 6, or minus 30 degrees. Now I've done something wrong here. Who can tell me what it is? Yeah, this is a great comment. Math with polar coordinates lines up really well with math involving vectors. And why is that? Well, because a vector is a quantity that has a magnitude and a direction. And polar coordinates is just very explicitly describing things by a magnitude and a direction. The distance from the origin and the direction measured as an angle up from the x-axis. So what's my mistake here? Yeah, it's about the bounds of inverse tan. The inverse tangent function always returns an angle between negative pi over 2 and positive pi over 2. But if the x value is negative and the y value is positive, that's in the second quadrant. So I guess if I just sketch some axes, minus pi over 6 is over here. So the inverse tangent actually gives me completely the opposite of the correct answer. At least the nice thing is that with inverse tangent, if you don't have the right answer, if you're pointing in the wrong direction, you just add pi to get the correct answer. So theta is actually pi over 6. So the point is, uh, 6 comma 5 pi over 6 in polar coordinates. The other way is easier. Like if I give you the polar coordinates of a point, like, I don't know, 3 root 2 7/2 pi. X is just going to be r cosine theta, which is 3 root 2 times cosine of 7/2 pi, and y is r sine theta, which is 3 root 2 times the sine of 7/2 pi. The angle 7/2 pi has a cosine of 1 over root 2 and a sine of minus 1 over root 2. 7 pi over 2 is in the fourth quadrant, so x is positive and y is negative. Alright, so that's a crash course in converting between polar and Cartesian coordinates. Questions about this before we move on to work problems? Okay, if there are no questions, let's do a work problem. Tell you what, I haven't run any ads in a while, and I just want to make sure that Twitch doesn't run an ad and interrupt me while I'm showing you some math. So I'm gonna run a 30-second ad right now while I write out a problem, and that way, hopefully, I don't get interrupted by an ad when I don't want to. All right, see you in 30 seconds. Oh, did it go? Okay, so let's empty a tank that's full of water. Let's say the tank is 10 feet long, and let's say that the cross section looks like, ooh, let me draw a better picture. Say that the cross section looks like this. It's a trapezoid. We'll say this side is 3 feet. Let's say the top is 6 feet, and maybe the height is 4 feet. Alright, so to empty the tank, we need to raise all of the water up to the level of the edge, the top edge of the tank, so it can spill out the side. And as always, the strategy for any of these Calc 2 problems is to look at just one little bit at a time, and then add all the results together using an integral. Okay, so let's look at one little horizontal layer of the water in the tank. Jacob, thank you for the 1 bit. And what makes it easier to consider just one thin slab at a time instead of the whole tank is that this little slab, all this water, is essentially at the same height. So it takes, it all has to be raised by the same vertical distance, and that's, a lot easier to think about than the entire tank at a time. So we'll say that it has a height of dy. Maybe I'll use a coordinate system where y equals 0 is the bottom of the tank, and y equals 4 is the top of the tank. And so I need to find the volume of that slab. That's going to be the part that involves the most work. So it's length times width times height. Only one of those is hard. And it's the length here. But we know that sort of the width going back into the tank, the width is 10 feet because we're told the tank is 10 feet long. And then the height is dy, but it's this length here that takes a little bit of work to figure out. Because when y is 0, the width is 3 feet, but when y is 4, the width is 6. There are different ways to think about what this is. I'm trying to think what would be the argument that you would see in Calc 2. If anyone has an idea, feel free to, and please suggest it in the chat. There are several ways to think about it. One is it's sort of a weighted average of 3 and 6. Depending on, or the weight depends on how far up the tank you are. There's a nice geometric approach based on similar triangles. Which is to say, if this is y, and if I call that x, then x over y is equal to, well, I guess I need to know what this is. That would be 1.5. Because the whole thing is 6, this is 3, so the left and the right portions together are also 3, so each one of them individually is 1.5. So x over y is 1.5 over 4, meaning that x is 1.5 over 4, which I guess you could call that 3/8 of y. And then this total width is the middle 3 feet plus x plus another x over on the left side. So that would be 2 times this 3/8 over y. Or sorry, 3/8 times y. Maybe I'll call this volume dv. So dv is 10 feet, and you know what? I'm going to stop writing units. We can just figure out the units at the end. So 10 times dy plus 3 times, or times 3 plus 3/4 y. And let's just make sure, is it 3/8 because there are 2 triangles? Well, each one of them was 3/8 of y, but when I add those 2 3/8 together, I get 3/4. Let me just check that my formula works. When y is 0, I just get 3, which is correct. And then when y is 6, sorry, when y is 4, which is the maximum height of the tank, 3/4 times 4, oops, sorry, 3/4 times 4 would just give me 3, so 3 plus 3 is 6, which is what I expect. Now that we have the volume, we can think about the work required to lift this horizontal slab of water to the top of the tank. Well, work is force times distance. Force is mass times weight, because we're counteracting the gravitational force. Sorry, I said mass times weight, but that's not right. The force is the weight. It's mass times g. There's a question, hang on, a bit confused on how it went from 1.5 over 4 to 3 over 8. Oh, yeah. 1.5 over 4. If I multiply the numerator and denominator by 2, that gives me 3 over 8. I just didn't want to deal with that decimal. So hopefully that clears up the confusion about that. If it doesn't, please let me know. I'm happy to re-explain it. So the force is mass times the gravitational constant g. And mass is volume times density. So I have volume times density times g times distance. Now I think I can finally say what all of these quantities are. The volume we just worked out is 10 times dy times 3 plus 3/4 y. The density, I'm just going to call it delta. It's some constant. Depends on what the tank is filled with. G is that gravitational constant, 16 feet per second squared, or 9.8 meters per second squared, depending on what unit you're working with. And then the distance, going from a height of y up to a height of 4 feet, that distance is going to be 4 minus y. So that's the work for this one horizontal slice of the water. And as we've seen, once you figure out the answer for one little piece, literally all you do is write an integral sign in front of it. Because we're just adding up all the pieces. Okay, I guess you also have to add bounds. And I've got 10 delta g, I'm just grouping all my constants together at the front. I've got 3 plus 3/4 y. I've got a 4 minus y. I'll put the the dy at the end. And then my y values are ranging from 0 at the bottom of the tank to 4 at the top of the tank. And there we go. Is there a reason that the topics on midterm 2 seem very disconnected from each other? That's a good question. I'm not the right person to answer that, because I'm not actually teaching Calc 2 this semester. I couldn't tell you why they've grouped the topics the way that they have. But yeah, Calc 2, honestly, even as a whole, just feels sometimes like a whole collection of disjointed topics. But at least all of the, I hope I'm convincing you that with pretty much all of these applications of integration, it's the same strategy in all of these cases. Like, if there's ever a situation where, you have a hard task, but if you just break it up into a bunch of little pieces, and if each one of them individually is easier to work out, then you can combine all those answers to the little problems together with an integral. So that's pretty much everything you've done in Calc 2 so far. Arc length. It's hard to figure out, the length of a curve, but if I break it up into little pieces and I pretend they're all straight line segments, well, I can find the length of a straight line segment, and then I add them all together with an integral. Work. I look at how much work I need to do for one little piece, and then I add them all together with an integral. Volumes of revolution, or cross-section. Any of these volumes, you're looking at little pieces of the volume, whether it's sort of horizontal or vertical slices or cylindrical shells. You're looking at little pieces where each of the little pieces is easier to figure out the volume of, and then you add them all together with an integral. Really, everything you've done so far is the same sort of scheme of solving the problem. And then, of course, the few weeks that you spent on integrals at the beginning of the semester, on integration techniques, that was just to be able to actually do all of the integrals that we end up with in all of these applications. So it all kind of fits together in a way. But yeah, it's a lot of different topics. So here's a work problem. We've computed this integral. We've written out the integral. To actually compute the integral, I would FOIL this out. You get a quadratic function. You anti-differentiate it. You'll get a cubic function. Plug in 0 and plug in 4 and subtract. It's nice integrating a polynomial, because when you plug in 0, that goes away. So this one shouldn't be too bad. So there's a work problem. It's about 10 o'clock. So are there any last questions before we call it a night? Sharky and Rev, I'm really glad that these are helpful. Thanks for watching. Thank you everyone for humoring me and joining me on this very long and intricate journey of working out the equation of the Brachistochrone. I think it's just one of the coolest problems, and I hope that you find it interesting. If you have any things that you would like to see on next Monday's session, if anything comes up over the next week in class that you'd like to see more about, shoot me an email or just send me a message in chat next Monday. Big Ducky Snow, you're very welcome. Thank you for viewing.